because
All
I
right.
just sent.
Yeah, I just did it now. So we're live, but I don't know if anybody's going to be watching it. Hello, everybody. We've had some technical difficulties. We're broadcasting live, and we're trying to correct it now. Here we've got some people coming back on.
Yeah, okay, we're live. Just to explain, we were trying to set up the Hangout. Tony was setting up the Hangout and apparently crashed before we went on air just before, and we had some issues trying to restart it. So we're gonna wait a few seconds for folks to join. I see George just joined, and then Padi and Harley will probably join momentarily.
Yeah, and we are really sorry about this. I hope you guys can find it okay. This was a issue with the Hangouts on air, which I've been having a lot of lately, and I'm working very hard to get away from this technology, as it is disappointing me more than it's not. So we're going to just give it a few minutes while people get connected again to the new Hangout on air, and hopefully you guys will be able to watch this.
Yeah, unfortunately, it's not streaming on YouTube or on, because I think it's the long.
Well, there's a new link. So here's the new link, Alberto. Let me put it in the group chat.
Okay, put it in the group chat. I can share that new link for that.
Here's where the new thing is being streamed. Okay, so hopefully people will watch it. A few people are catching up. I have to get a. Let me just put this here.
Okay.
All right. So,
at least it's going to be archived, right?
Yeah, this will be. Yeah, but unfortunately, I wanted to get the live viewers also.
I know.
Okay, so there's this. Now I have to go to the Hangout page, and I need to get the chat window popped up. Pop out chat. Okay, I've got that. Now close that window. Okay, good. All right, guys, we're back. Sorry about that. That was very frustrating. But we want to get started because we're 15 minutes late getting going. I'm terribly sorry. But let's get started right away. Hopefully we'll get more viewers as time goes on.
So we're missing Padi, but I think we should continue.
Oh, you're right, Padi. I wonder if she hasn't gotten the. Could you guys send the Hangout link? Can you try just one more time, Alberto, while I get going? Oh, there she is. Okay, she's joining. All right, very good, awesome. Phew. All right, what a relief. We're back on air.
Okay, welcome everybody. Let's restart.
All right, let's go. Hello, everybody. Welcome to this month's Future in Space Hangout. My name is Tony Darnell. I run DeepAstronomy.com, and this month, I am extremely excited about this Hangout, and that's what makes these technical difficulties so frustrating, because we are going to be talking about NASA's TESS mission. And this mission is very exciting to me because it promises to extend our knowledge. TESS, by the way, stands for the Transiting Exoplanet Survey Satellite. And it will be launched later. And we're going to talk about when it's going to be launched. We're going to talk about what it's going to be doing, what it's going to be looking at. But as its name implies, it's going to be looking for exoplanets, much like what the Kepler Space Telescope did. And it promises to expand our understanding and knowledge of Earth-sized exoplanets in a way that can only be rivaled by Kepler. So this will be an exciting time coming up, and I can't wait to talk about this mission. And before I do that, I need to get my co-hosts introduced with me, and the man who puts these things together is Dr. Harley Thronson from NASA's Goddard Space Flight Center. He's an astronomer there. Hi, Harley, and welcome.
Yep,
Also with me, I'm rushing through this, is Alberto Conti. He is Dr. Alberto Conti. He is the innovation scientist extraordinaire at Northrop Grumman, and so that would be he's joining us for this Hangout. So welcome back, Alberto. Okay, so these Hangouts, usually I go a little bit longer into the introduction, but these Hangouts are both sponsored and endorsed by the American Astronomical Society and the American Astronautical Society, and we are very excited to have them on board to help us understand and get the word out about the latest NASA missions. So this is a chance for the members of these organizations to get the word out on them. So, okay, let me get to my guests. Let me get to my Hangouts, or to my guests. We're going to get started on the topic right away, but if you guys want to hang out just a little bit toward the end, I'm going to talk to you a little bit about some changes I have in mind for the Hangouts on air going forward. So if you want to learn about that, just stick around after the Hangouts over. Okay, with me are my guests today, Dr. Patricia Boyd, also known as Padi. Hi, Padi. She is the Guest Investigator Program Office Lead at NASA's Goddard Space Flight Center. She's also the Chief of Exoplanets and Stellar Astrophysics Laboratory at Goddard, and she's not so much anymore, but the HST Deputy Project Scientist for Operations. So welcome to our Hangout, Patty. I'm excited to have you here. Also joining me is Dr. George Ricker. He is the Principal Investigator for TESS. So there you go. And he's also the Senior Research Scientist at MIT. So welcome, George. Thanks to both of you. Let's give our viewers a little bit of a background in what TESS is going to be doing first. Now, George, I think I'll start with you on that since you're the Principal Investigator. Can you tell us a little bit about what TESS is hoping to accomplish, what its primary goals are?
Yeah, well, the principal goal for TESS will be to conduct the very first all-sky survey for exoplanets, and it's with a special focus on those that are relatively close to the solar system, that are in the solar neighborhood, so to speak. The total amount of sky that TESS will be able to cover in the first 2 years of its mission is about 400 times larger in solid angle than did Kepler. And it's expected that we'll be looking at objects that are within systems with planets and their host stars that are within a couple of hundred light years of Earth, whereas typically the systems that Kepler was looking at were several thousand light years distant. So as a result, the objects that we'll be looking at, the planets and their host stars, will be a lot brighter, in fact, typically about 100 times brighter for follow-up observations. So the key thing for TESS is to identify the objects so that they can be followed up with missions like JWST that'll be coming in the future, as well as the upcoming generation of 20, 30, and 40-meter telescopes. So that's the exciting thing that TESS will actually do in terms of opening up a totally new horizon for the study of exoplanets.
So as many of you may remember, and if you've watched this channel for any length of time, you know a lot about the Kepler Space Telescope, which is now operating as K2. It stared at just one spot in the sky in the constellation of Cygnus, and it was looking at roughly 160,000 stars. And it did it by this thing called the transit method. And Patty, I would like to, can you give us? I'm going to put up the little animation. Maybe you could talk a little bit about how TESS is going to find these exoplanets.
Sure. So we're also going to be using the transit method, and it's a wonderful method for finding exoplanets because you can learn so much about the system just by measuring some very fundamental properties of the transit. So a transit happens when a planet passes in front of the face of its star as it's seen from Earth. And this only happens for planetary systems that are aligned with respect to the Earth so that we'll actually see that planet cross in front of it. So it's not all planetary systems will do that. Actually, very few of them do. But if we're lucky enough to be lined up, we can actually measure that very tiny dip in the light from the star. We have to have very precise measurements to be able to do that because the dip from a planet is quite tiny compared to the light from the star. And if we see one transit and we can measure its depth, that gives us a sense of the size of the star, or the radius of the planet with respect to the star. And then if we wait and we measure the next transit, then the time between those two transits is telling us the orbit of that planet. And we actually typically wait until we see 3 or 4 transits so that we can really nail down that orbit. And that's basically how we discover planets with the transit method.
And another thing you can get from this is that if this dot is bigger, then this dip is bigger, and you can get a little bit about the size of the planet itself, the physical size of it as well. So you get the orbit information by the differences between these two pass-bys, as well as some size information. Now, this has a bias to it, obviously. You're not going to see it if we're not looking in a way that where the planet passes between the telescope and the star. So there is a bias there. We're going to miss a lot of stars. But this, instead of looking in just one area, we're looking at the entire sky. Now, how fast, Patty, how long will it take to make a complete? And I'm going to put this this video up too. Yeah. But I was, to scan the whole sky, how long might that take? Let me put
to get the entire sky scanned by TESS?
Yeah.
So it's going to stare in segments. Each of those segments lasts 27 days, and it's like a strip on the sky that's just a little bit above the ecliptic plane. It'll go all the way past the ecliptic pole in a strip that's 24 degrees wide. by 96 degrees long. And then after 27 days are complete, the spacecraft is going to turn and stare at another observation sector. So you now see them there stepping across the sky. There's 13 observation sectors in one hemisphere of the sky. Then the spacecraft will rotate after that first year, and then it will survey the entire, the other hemisphere of the sky in another 13 segments. That will take 2 years.
Okay, so wow. Okay, so so one of the things that I recently was pointed out to me is that dip in brightness, the brightness of the star compared to the planet is very small, and so do you need to look at certain size stars? Are some stars better than others? The bigger the star, the brighter it is compared to the planet, right? So presumably it would be harder to see the dip. Is there any preferential star size for this technique?
Are you asking me or George?
Anyone.
Either one.
Okay.
Either one.
So I think this is, I think it would be great if George could jump in here and talk about why TESS was chosen to be sensitive in the region of the spectrum that it is. And it's specifically to go after certain type of stars. We think this is going to be really rich.
So before George goes and answers the question, I was going to say that the video that you showed, Tony, is extremely exaggerated, right? So we're, we might want to point that out, that, the little planet is causing, a much smaller dip like we've seen through on Kepler, for example, order of 1%. Go ahead, George. Sorry.
Well, the range of that dip, as you said, and Padi commented, is small. For a Jupiter-sized planet transiting across a star like the Sun, that dip is of order 1%. Whereas if you were to have an Earth-sized planet pass in front of the Sun or a solar-type star, that dip might be approximately 100 parts per million. So it's a lot smaller. It's like 100 times smaller in terms of the size of the dip. That means that if you're looking for Earth-sized planets, let's say, you're going to, in order to make the problem a little easier to solve observationally, that you'll tend to look at smaller stars. And it turns out that smaller stars are actually in a spectral class that astronomers refer to as either K stars or M stars. These are stars, in the case of M stars, for example, that have temperatures that are maybe half that of the Sun, and their sizes are also about half or perhaps even smaller than the Sun. So one of the things that happens is that since they're cooler, their emission tends to come out in the red portion of the pass band, or in fact even in the near infrared. And that means that we want to really focus on stars that are both smaller than the Sun and cooler. And it turns out that nature was actually very kind to us in this respect, because that actually is the most common type of star in our galaxy. There's something like 3/4 of the stars that are in the solar neighborhood are these smaller, cooler stars. And then one of the other virtues of this is that the dip in brightness that you get from the transit is actually deeper, because the diameter of the star itself is smaller. But more often, if you're interested in potentially habitable zone planets, it turns out that the transits will actually occur more often, because in order for that to take place, the planet needs to be closer into its host star in order to get you above the melting point of the melting point of ice, which is sort of a broad definition of what habitable zone might actually mean. So all these things were taken into account in the design of TESS and the cameras, so that it's really optimized to operate in the pass band of light that's very difficult for us to see. And in fact, one of the things that we actually had to do at MIT when we were building the cameras is we had to make our own CCDs. And the item that I'm showing here is an 8-inch wafer that contains a fairly large number of such CCDs. The elongated rectangles that you see, which are about 6 centimeters by 3 centimeters each, in this portion.
George, can you point it toward the camera a little bit? We see a lot of reflections.
There we go.
Oh, there you go.
There you go.
Perfect.
Part of the reasons that you see so many reflections is that these CCDs and the structures that are on them act as a little diffraction grating.
Right.
So that's actually a neat thing that happens. So in any case, we've made several hundred of these, and then picked the very best ones. And they're unlike the CCDs that you might have in your digital camera, in that they're much thicker, and that means that the light photons that come in are much more likely to interact and be registered in, as signal photons. And so that's really one of the key things with TESS, as well as the observing strategy, which Padi described earlier.
Now that is a CCD. That is the size of a lot of people.
I'm looking at my iPhone here.
That's the diameter of a C8 telescope at home. So
Exactly.
that is huge. All right.
So
Well,
I'd like to add one thing to what George was talking about as far as M-stars go. So you know that they are smaller and they're cooler, so that when a small planet like an Earth-sized planet or a little bit bigger passes in front, that makes a deeper transit than what we were looking at around like a sun-like star. But the other thing that's really exciting over the last couple of years is that we're discovering that M-stars actually can make Earth-sized planets or small planets very readily. So we're really expecting that there's going to be a tremendous number of small planets around the M-stars with TESS.
So maybe you guys mentioned this, but how many stars do you think you're going to be able to look at? Hundreds of thousands. Kepler look at 170,000 or so targets. So how many of those are you going to look at? And in particular, you would just mention that the smaller ones might be actually more interesting. So how many of those, the red dwarfs, the cool dwarfs, you're going to be able to see?
Well, the total number of TESS actually will have two different ways, two different modes in which it will operate and detect planets. In one of the modes, which we refer to as a postage stamp mode, there will be stars that we know about that are previously targeted, and there will be a total of something like 200,000 of those that will be surveyed in the entire sky. But then the satellite also has another mode in which we are able to take full frame images in which there's no pre-selection at all, and the total number of stars that will be in those images to be examined and sent back to Earth for follow-up is 20 million stars. So it's a huge increase quantitatively over the numbers that it was possible for Kepler to actually study.
and Padi,
which opens up an incredible space for discovery. So that's astonishing.
Right.
That's great.
So Padi, you sent this graphic over to me. I'm going to go ahead and make it big. This is sort of what this is kind of a follow-up on what this what TESS is designed to actually see, which are Earths and super Earths that are orbiting bright stars and these M-class stars. Can you describe this? Talk to us a little bit about what this is showing us.
So the message in this plot is basically, it's a graphical comparison of the types of planets that Kepler found versus what we expect TESS to find. So the planet's radius is on the x-axis or the bottom. If I click on that thumbnail, will it bring it?
Yeah, it'll be big for you.
Okay,
Yes.
there we go.
Yep.
So that's in terms of the radius of the Earth. So the Earth would be 1 on that x-axis.
Right here.
Yeah, and so it goes up to 10 or so Earth radii, so that's getting bigger in that direction. And then on the y-axis is the host star's magnitude, so how bright it appears to us on Earth. And you can see that Kepler's planets are in the blue, so they are fairly dim. You need a telescope to see them. In many cases, you need a very powerful telescope to really get additional information about these planets once they're discovered by Kepler. In comparison, the TESS planets discoveries, those are the red ones. So they are going to be around much brighter stars typically. And this is really great for us to take the next steps because we want to characterize these planets. We don't just care about how big they are, what is their radius, but we want to know what are they composed of? Do they have atmospheres? Might they have chemicals in them and molecules that would hint that they were habitable? And that's the type of information that you get by following them up with larger telescopes. The more light we have from these planets, the easier that's going to be for us. So this basically tells you that the TESS planets are going to be much easier to follow up than the Kepler ones.
Okay, so but TESS as a spacecraft is not going to be able to characterize these atmospheres, right? It's going to identify the stars, or the planets, and then go to ground-based observatories or even, you know,
GWST, right?
well, it's not launched yet, is it now?
Well,
We can't wait. So that's why TESS is the discovery machine.
Yeah.
But you know, Hubble Space Telescope is making groundbreaking discoveries and in characterizing transiting exoplanets right now in ground-based observatories as well. So the Spitzer Space Telescope. So we're really hoping to be able to use all of these follow-up resources at our disposal. And then when James Webb launches, we're extremely excited because TESS is designed to really maximize planets in the James Webb Continuous Viewing Zone.
Oh yeah, I wanted to go back to that because I didn't understand that. I'm going to put that back up again very
While you're
briefly.
putting it up, let's let the audience know when the expected launch date of TESS is.
Okay, we will. I want to get to that. I promise. I will talk about the launch, but I wanted, since we're talking about science, real quick, I want to finish this up real quick. What does that mean down here? It says the JWST. This is, by the way, the scan of the sky that video was showing. These are the sections that George was telling us about. What's this JWST? That's where JWST will always be looking,
Or can always be looking.
or can look.
Or it's always accessible to it.
correct.
Okay, all right.
Yeah, the area that's enclosed by that dashed line near the pole is, as Harley says, that JWST can look at that at any time throughout the year. There's another region that goes down to sort of mid-latitudes in this ball, about 45 degrees mid-latitude, where JWST can look at those objects anytime within something like half a year. So the focus of the pointing strategy for TESS is to optimize for this region of concentration of targets that will be in either the northern ecliptic pole or the southern ecliptic pole, with just that in mind. And that color code on the right-hand side shows the number of days per year that TESS will actually be staring at that particular patch of the sky.
So mostly up here, but
exactly.
Okay, I get that. Okay, very good.
And I put up exactly what JWST does, Tony. If you want to click on that, it basically shows the continuous
got it.
zone,
Okay.
right? So you can actually see the top, what George was talking about, the continuous coverage zone at the poles. You can,
That up there at the top. Okay,
Yeah, correct.
Very good. Okay, well, all right. So as Harley pointed out, we should probably get to the mission itself. Now, there's been some changes in the mission program. If you go to this, if you notice when I was showing this earlier, I was showing you this video. If you notice, right up here, there's this guy named DeepAstronomy who put up a video, made a video about TESS, and you feel free to go watch it if you like. But in that video, he said, that DeepAstronomy guy, that the launch was scheduled for August of 2017. That information is no longer true. So, George, can you tell us what is the status of the launch of the TESS mission?
Well, the current status for the launch itself is related to when the rocket that we're going to fly on is going to be available.
Which is what?
It's going to be a Falcon 9.
Okay.
And it'll be launched from Cape Canaveral. And there's
I'm going to be there, by the way.
There's going to be a very well. I think we all are.
Yeah, get in line, Tony.
Yeah, I live here. I'm going to be there. I'm going to see it one way or the other.
Right. Well, there's also going to be some poor souls that are going to be stuck at consoles in Virginia and Maryland and various other places, and so those are the unlucky souls. So, but in any case, the preparations for the launch were originally, as you said, August of 17, and then there were some delays in the vehicle and a number of other complications that pushed that to December. But now, as a result of the other complications that have affected the availability of the Falcon 9, the launch has been pushed off to March of next year. So it's just in fact almost exactly a year away from now. So
That's
we're all thinking about it.
So why does the website say you're shooting for March, but no later than June? Is that just give yourself some wiggle room there in case something happens?
Well, there's always uncertainties in the launch schedules because SpaceX has got a lot of customers for the rocket. It's a great rocket. We were really happy that it was selected for our use. But at the same time, when something's popular, sometimes there's other people in line in front of us, and so that's basically what's happened. The significance of the June date is that's the end of a planning date that NASA has imposed on the mission.
I was going to ask, George, do you have a particular window when you have to launch, or?
Well, the answer is we do and we don't. TESS goes into what's called a lunar resonant orbit.
Yeah, I just put it up actually. That's exactly what I was going to ask, because it's a beautiful, interesting orbit actually.
Yeah. Now this is an orbit that we actually developed specifically for TESS. No satellite has ever flown in this orbit before, but the orbital mechanics are well enough understood that we were able to convince ourselves and NASA that it was going to be a reliable way of going about it. But basically what we do is we actually go into these 3 orbits. I'm not sure if you can see what I'm pointing at.
They're in well, no, we can't, but Alberto will points.
Okay, good.
We can do it. Go ahead.
So the 3 green ellipses with one common point near the Earth are what are called phasing orbits. And basically what we do is we launch from Cape Canaveral into that lowest orbit, which is at an altitude of an apogee of about 200,000 kilometers. And then over the succeeding 2 orbits, we actually raise the apogee by doing small burns at perigee, which is the way orbital mechanics works.
Yep. And
then we do a flyby of the moon. And the purpose of the flyby is to basically go into that large looping orbit that's partially pink, and then it turns yellow. Yep. And that looping orbit does 2 things. It changes the inclination of TESS's orbit so that it's not exactly in the same plane as the Earth and the Moon, and as a result, we don't have problems with the Earth or the Moon getting in the field of view as the mission unfolds. And then the other thing is, once the orbit is fully set, we're it's an eccentric orbit, but it goes out at apogee about to the same distance to the Moon, but it's arranged in such a way that when we go out to that distance, the Moon is not there. The Moon typically will be 90 degrees away in its orbit from us. And since the period of the TESS orbit is half of a lunar month, you basically use the Moon to stabilize the orbit. And we ran some very careful simulations that showed that we can stay in this orbit for the order of a century and not have to use any propellant or anything.
Is that right? Oh, wow.
And we end up coming close enough to the Earth at perigee that we can run downlink rates for our data of about 100 megabits per second.
Yeah.
So that's a very high data rate for a relatively small satellite.
So what's the typical ellipticity of the orbit?
The ratio of apogee to perigee is about 4 to 1. So it's 17 RE to 60 RE.
George, I hate to interrupt you, but what microphone are you using?
I'm using the one that's associated.
Okay, that's rubbing quite a bit against your tie. So
okay, I'll try to move it away.
That's much better. Thank you very much.
Yep. Thank you.
So as far as you know, I find it interesting actually, is that no one has ever used this orbit before.
Well, there's a similar orbit. This is called a P/2 orbit.
Yeah.
There's a mission called IBEX, which is a heliophysics mission that uses a P/4 orbit, and it was actually its orbit was adjusted in the post-primary mission phase to be. It actually makes 4 revolutions in 1 lunar month, so its period is roughly 7 days.
So I can tell you that us and Earth, we've looked at this orbit because it's a really cool orbit for what you want to do for similar. You can imagine similar missions doing having a lot of time and taking advantage of the orbit. So it's a really cool orbit.
Yeah, I didn't.
Very clever.
It really is a cool orbit, and one of the things for the radio heads out there, you actually have a communications advantage for this orbit over Earth's Sun L2, which is another place that a lot of science missions are going to now. This gives you a 23 dB communications advantage. So because you're coming in so close at perigee.
Yes, absolutely. So good.
All right. Well, okay. So I want to remind everybody, after much wrangling of technology, you are watching the Future in Space Hangout that we have. We have these every third Thursday of every month, and our guest today is the principal investigator of the NASA's TESS mission, Dr. George Ricker, as well as Dr. Patricia Boyd, who is she is the guest investigator, program office lead at Goddard, as well as the chief of exoplanets and stellar astrophysics laboratories, also in Goddard. So that's who we are talking to and what we're talking about. And Padi, I'd like to ask you about some of these. You sent us some interesting science plots that talk about what we know about exoplanets now versus what TESS is going to show us. I want to put those up a little bit. Maybe you could talk a little bit about them, and then I'm going to get to some questions and comments from some of our viewers. So I want to put this up a little bit. Maybe you can help me or help us understand what these are all about. These you were telling me some interesting things before the Hangout started about this.
Right. So this is actually a graphic that was made by his name is Alberto Thronson, and he was a postdoctoral fellow at MIT. He recently left to take a job at Colorado, but he made some beautiful overview graphics about the situation for exoplanets today versus what we're expecting with TESS. So what we're seeing here, there are blue circles and there are black circles. The black circles are exoplanets that have been discovered from ground-based surveys. So you see that they're close. The distance is on the x-axis again. So these are ones that are fairly close to the Earth if they're at 10, the black ones. They're 10 parsecs away. And then the blue circles there are from the Kepler survey. So Kepler discovered a tremendous wealth of exoplanets and exoplanet candidates, well over 4,500 exoplanet candidates coming from the Kepler mission. But what you notice in this graphic is that they're all pushed very, very far from us, 1,000 parsecs or further. Is where that most of those discovered planets are. So what we really want to have are exoplanets and exoplanet candidates that are closer to Earth because we get much more photons from them. They're brighter. We can follow them up more easily, as we were showing before. So if you show the second plot, those are the in orange are the expectations of what TESS will discover. And so they're based on what we know now about exoplanet populations from missions like Kepler. And we just extrapolate that to the sensitivity of TESS and the type of survey that TESS is going to do. And what you see there is that TESS is really going to fill out that missing space there and give us a tremendous number of candidates between 10 and 100 parsecs. So those are the ones that we're going to be really excited about going after with the bigger ground-based telescopes to look at details of their atmospheres and get the masses of the planets.
And here's the, as Alberto and Harley were pointing out, here is the TRAPPIST system that we've all learned so much about. It's relatively close, relatively small. This is kind of the sweet spot down here, and TESS will be helping us to find a lot of the planets in that area, as well as some of these at closer to 100 parsecs. I didn't realize Kepler had found so many so far away. I thought they were closer, but that's...
Well, it was designed to do that because it was a statistical mission, right? So they wanted to be able to look at, they were looking just a 10 degree by 10 degree patch of the sky, but they optimized it so that they could go after 150,000 stars at once.
So it's like 3,000 light years, and then what you do for TESS is 300, basically, right? You go much closer, much brighter, and you characterize. As you showed, I think it's going to be incredible to fill all that, the space right there.
All right, so I'm going to look up a little bit here on the chat window. Unfortunately, I'm just using... Uh-oh, my dog is running it out. On this Hangout.
We're all a big family.
Yes, exactly. Adam Synergy, welcome back. Adam, will TESS look at young stellar objects and open star clusters?
Absolutely. TESS is going to look at everything. So there's a group, very active group called the TESS Target Selection Working Group. Yeah. And they meet every week, and they're compiling all the information we know about stars all over the sky that are of interest. And of course, young stars and clusters of young stars are really interesting because we are seeing exoplanets at an earlier part of their evolution. So there's a special subgroup of that Target Selection Working Group that is very focused on clusters and young stars.
Okay. And Swiss Milk is asking, Great handle. Will JWST completely rely on TESS on where to point?
No.
No.
Yeah, I don't think. But it is going to use TESS data, right, Alberto? I mean, if
Yeah. I mean, actually, we're really looking forward to TESS specifically because of what I guess we just talked about, the fact that you're gonna find the closest, most favorable, if you will, exoplanets around 300 parsecs are pretty bright. JWST will be able to actually start detecting atmospheres of some of those, right? But TESS by no means is the only asset that we have to tell us where to look, obviously.
And that's important. Go ahead, Padi.
I was going to say, I'm sure that the exoplanet community would be delighted if JWST used just TESS to tell where to point.
Bit of a bias there, wasn't it?
We could probably use all the time, actually. We're probably going to have a lot of candidates that we want a lot of follow-up. But the entire astrophysical community is so excited about JWST for all that it can do for astrophysics from exoplanets all the way out to the most distant galaxies.
Right.
So we're going to be competing.
Exactly, which brings up a good point, which is there's so many stars, so many galaxies, and so little time, for JWST and other assets that the competition is part of the game. You have to have a clever idea, and then TESS is gonna really open up some of that space, for us for discovery. So
that's right.
Well, one of the things I think that we're all very excited about for TESS is because it's surveying the entire sky, is that the discovery space itself is actually very large. And in fact, in addition to things like what Padi was talking about, young stellar objects and clusters and variable stars, there's even an opportunity for TESS to find surprising new objects that are going to be extragalactic in character. For example,
really?
With the magnitude limits that TESS will go down to in a 30-minute integration, there will be about 10 million galaxies that it will also detect. And these can include things like active galactic nuclei, things like Seyfert galaxies, which a lot of astronomers are interested in as well, supernovae that are on the rise, and then another very interesting phenomenon is what are called tidal disruption events, where a star is actually shredded by passing close to the black hole in the interior of a galaxy, and this produces a period of variability in its light that TESS would be able to detect all the way down to about 17th magnitude. So this is a huge discovery space that TESS will actually be able to cover, in addition to the focused activity on exoplanets.
But wait, I think there's more, right? You're going to be able to look at the stars, for quite some time. So you're going to be able to do seismology on the stars. Sorry,
Harley? I was just following up on what Alberto said. Stellar astrophysics.
Stellar astrophysics, but more to the point, astroseismology is a really exciting field because from the variations that occur in a star's brightness, when you have something like a flare that goes off, it will cause the actual exterior of the star to ring like a bell, and the character of the resonances are such that you can use to determine things like the run of temperature with radius from the interior of the star. So there's a huge amount of information. In the case of our sun, for example, that those characteristic vibrations or variations in brightness are about 5 minutes in character. But if the star is much larger, those variations might have periods going up to 30 minutes or so, and then they're classical variable stars like R. Lyrae stars and Cepheids and lots and lots of things that can be studied in these 20 million objects that I think a lot of people are thinking about.
Okay, Buddy Lauder has a great question I meant to ask, and I'm so glad that I've got this chat open so that you can get people to remind me. I got so flustered with the start of this Hangout. Buddy Lauder is asking, what is the expected operational lifetime of TESS? We've talked about when it's going to be launched, but how long is it going to be up there?
Well, as I said before, the orbit itself would probably keep it up for many decades.
I think that's amazing. I didn't realize that orbit was going to let it stay up there with no propellant. That's really cool.
Right. Well, we have to launch at the right period of time. There are 4 or 5 launch opportunities every month in which the moon and the rotation of the Earth are aligned correctly for us to get into this orbit. But those are things that we can manage. But as far as the duration of the survey, as the animation that Padi showed indicates, we'll be able to carry out the primary survey in 2 years' time. So we'll do the southern hemisphere in the first year and the northern hemisphere in the second year. And so that's what NASA calls the primary mission. But going beyond that, we'd be very excited to be able to continue looking at different parts of the sky with different degrees of concentration. Because even though the survey is initially designed to concentrate, to find a large number of candidates for JWST at the north and south ecliptic pole, we can adjust the overlap in the fields of view in subsequent missions to find other phenomena with other timescales as well. So I think the real key is the amount of funding that NASA is willing to place for an extended mission, and that could be, if we do our job right, that could very well be a decade or more.
That's kind of like what they did with Kepler and K2. I have this slide that kind of shows the timeline of some of these missions. Now, most of these are still actually all of them are still up. Hubble is still up. Spitzer is still up. You've got Kepler and K2 still taking data. What they've done with that telescope just blows me away. I love the fact that they're using the solar wind as a reaction wheel. And then they've got, and then here comes TESS coming up next year in about a year. And of course, from what I understand, George, then basically it's just a matter of how long NASA wants to keep paying for it and how long it keeps running. And because it's going to overlap with JWST and possibly even W first. So that would be amazing to have all these telescopes up at the same time. I mean, that would be great. Spitzer is still there. That's remarkable too.
Right.
Yeah.
Well, for example, if we launch in 2018 and we're still operating by 2028, that would overlap pretty much with the primary mission of JWST and into the beginning phases of the following
W first, yes.
On W first.
W first. Yeah, that would be great. And we'll, of course, like all NASA missions, we will go to the senior review with the other missions after our prime mission is over. And I'm expecting that we're going to have so many exoplanets results and also all the other science that TESS can do, the time domain astronomy that George was talking about before, that we're going to go into that review very strong. And I think that will be a
and don't forget, as you mentioned, actually, Hubble is still going to operate, hopefully at the beginning of our next decade. So that's going to be also incredible because it has done a lot of exoplanet science lately. So
having Spitzer, Hubble, and JW at the same time would be amazing.
Let's do it. Okay. So I want to mention, I put the link. Well, I had the link in the old Hangout. If you go to test.jsfc.nasa.gov, you'll find on there a downloadable paper model that you can do. Now, this was built by the guy who actually designed the paper model itself. This is a TESS spacecraft minus the solar panels. I haven't put them on, but this was made by John Joggers, I think is how you pronounce his last name. But he's made these for a lot of missions, and what you can do is download this model and print it on cardstock. Here's one for Gaia, which I haven't built. But and then you can build these things. I mean, this is really cool. But not to be outdone, of course, the principal investigator has one of himself. Why don't you show yours? Yeah. So, and that was. Did you say that was 3D printed?
Yeah, this is 3D printed, and it's been painted very nicely. It has all the different features of the satellite. Mine has the solar panels.
Yeah.
And you can actually see this is a sunshade, and you can see the four lens hoods on the cameras in the top. And there are a lot of details on this.
Oh, there you go.
And there are some and some of the images that are on the web actually have some of these details as well.
Right, but yeah, you can get a really good feel for it with that paper model as well. So,
Right.
and then Patty, you have one behind you there.
Not to be outdone, exactly.
Yes.
Mine is little.
Exactly.
Yes.
Mine is little and white, but it was also done with a 3D printer. And I believe the 3D printer model is also online.
I was going to ask you that.
That's right.
Yeah.
So is that on your website then?
It is on one of the TESS websites, yeah. I think
Okay.
tess.gssc.nasa.gov. And you can see the 4 cameras here. But I think one of the things that's really exciting about now, and that we're getting very close to being 1 year out from launch, is that all the pieces of TESS are really coming together now, right? George can tell you more about how the cameras are now being tested and the spacecraft is being tested. But, you know, all these things that we've seen on PowerPoint charts and in animations over the last few years, they're actually all coming together now. Very exciting time.
Yeah, let's talk about that a little bit, George. So how are things coming together on the
Well,
spacecraft?
they're actually coming together quite well. As Patty said, there are 4 cameras, and you can see that in this model here quite nicely. And each one has its own independent optical assembly. There's a lens, there's a focal plane with 4 CCDs like the ones that I showed you in that wafer image, and all of its electronics. And the spacecraft itself, which is this hexagonal structure behind it, that's actually being constructed by Orbital Sciences, Orbital ATK, in Dulles, Virginia. So since the cameras are now nearing completion, they and the other instrument components will actually go down to Orbital in the next couple of months, and then then the instrument assembly, which is in this portion up here that I'm touching right now, that will be mated onto the spacecraft, and then it will undergo a series of thermal back and vibration tests to prepare it to actually go to the launch site, which will occur near the end of this year.
And where's it being assembled, did you say?
It's being assembled in Dulles, Virginia.
Okay.
Sterling, Virginia, I guess is what the town is called, by Orbital ATK, who is our spacecraft vendor.
And can you give us an idea of you know, how big is it? You know, we're used to hearing
Well,
JWST is huge, but this is much smaller. I know. So just to have an idea, maybe how much does it weigh? You know, what are the typical physical characteristics of?
Okay. Well, how tall are you?
I'm 6 feet.
Okay, you're taller than this spacecraft is.
I'm asking because I saw a model. That's what no, but that's actually, I want to stress that this is great because you can do incredible science packaging, you know, with small packages.
Yeah, the satellite with all the instruments weighs about 400 kilograms. So I suspect you don't weigh that much, but it's
no. Give me a few years if I keep eating this way. Yes.
I'm there. Okay, well, so I'll get to a couple more questions here. Cool. Oh, first of all, Hans Milling is commenting, cool watch, Alberto. So let's see.
I don't know.
John Suffel, thanks for joining us, John. I'm glad you could make it today. Will TESS look at Tabby Star? Well, someone had to ask, he says. Tabby Star, for those of you who don't know, is KIC 8462852. We've done a hangout on this before. It's in the constellation Cygnus. Anybody want to comment on that?
Well, it certainly will, because it's close to the Kepler field of view, if not in it, and TESS will certainly look at that field.
Okay, good question.
I think does it somewhat depend on launch date, George? Like, could it possibly fall between 2 observing segments if we get unlucky?
Well, it might, but I think that's at a high enough ecliptic latitude that the fields of view start to overlap. So we'll have that little star pattern that you were seeing indicates most of the gaps are going to be at lower ecliptic latitudes. Now, there is also a possibility that it might fall between gaps with the CCDs themselves, but that's something we'll just have to figure out.
Okay, both Larry Keys and Adam Synergy have some great questions. Let me do Larry first. Larry is asking, will you rely on citizen scientists to analyze any data taken from TESS? It's a good question. Will you guys do any citizen science stuff with the data?
Well, we certainly will, but there will be citizen scientists participating in the mission, but there's also a group of astronomers here at MIT and at the Harvard-Smithsonian Center for Astrophysics, and also another group at NASA Ames Research Center who are going to be involved in analyzing the data. And then we, in addition, have a network of ground-based follow-up telescopes that have all been lined up for TESS. In fact, they're part of the major mission that will provide what we call reconnaissance spectroscopy, so we can separate out false candidates, which might be due to eclipsing binary stars, for example, from true exoplanets. And that's all part of the mission. And then in order to find the very best planets of Earth size, that's going to require the use of precision radio velocity follow-up. And there are, at the present, there are a handful, 4 or 5 such telescopes worldwide that have been lined up to help TESS in that regard.
Awesome. And in a related question from Adam Synergy, and I want to expand on his question a little bit. He goes, who gets the data? And I'd like to also add to that, is there going to be is it like Hubble, where there's kind of an embargo period for the project at all? Or I guess it wouldn't be like Hubble in the sense that you take a picture for a certain scientist and then they get the data for a year. So who gets the data, and is there an embargo period?
There's no real embargo period, but it will take us a little while to get the data reduced to the point that defects or irregularities in the images can be subtracted out. But then it will be placed on a public archive at Space Telescope Science Institute, the so-called MAST archive. And that will occur on a time scale of a few months, and then it's available essentially to everybody.
Yeah.
Okay. And
then of course the other thing is there's a wonderful guest investigator program that, unlike many such Explorer programs in the past, will actually go online right away when the program starts. And Padi is the head of that, so she could comment on.
Okay, Padi, go ahead.
Some of that.
Yeah, so we're really looking forward to being able to make some of these postage stamps that George was talking about that are typically put onto stars looking for transiting planets. We're going to make those available, some of them, to the astronomical community, who can choose their targets based on what their scientific interests are. And that data will flow the same as the TESS data after the period when it flows through the processing pipeline to get calibrated. It'll be put at the MAST archive, and it will be public immediately. So I think what we're going to see is that there's going to be so much science coming out of TESS that the science team will be, very busy following up the exoplanets that they're discovering, but that there will also be an opportunity for the general community and amateur astronomers to get involved as well. Because remember, these are brighter stars, so they may even be able to go after, say, like the 3rd or 4th transits with their own telescopes. So I think we'll see a lot of activity on TESS data.
And MAST stands for Mikulski Archive for Space Telescopes. And Alberto, I think the URL is it mast.stsci.edu?
Yeah, you can go there to archive.stsci.edu.
Right, so that's where the data will go. Okay, very good. So Jay Cross has a really good question. With just a 27-day window, hang on before I ask it. I'm a little late, and I know I promised I would let you guys go at 4, but since we started late, is it okay if we stay a little bit longer, or do you have to go? If you have to go, I completely understand.
I could save about 5 minutes more.
5 more minutes. Thank you. Thank you, George. Thank you. Okay, so
Same
the question. Great. Thank you. Thank you, Padi. Jay Cross, with just a 27-day window for each patch of sky, how many planets are you likely to miss because the orbits are too long? That's a really good question. Will that be an issue with the K stars?
I can take a stab at that. The answer is it depends on the type of planet that you're interested in and what the temperature of the planet is likely to be. There will be no problems finding planets orbiting K stars per se if they're relatively close in to their host star, but the habitable zone for a lot of the K stars will be in the will correspond to orbital periods that are going to be in the range of 100 days or so. So it's likely that TESS will only find systems like that are close to the ecliptic pole, where the observation times that we have are many months to almost a year. So that is one of the factors that's come into play in the observing scenario. However, in an extended mission, we would have the opportunity to focus on a a smaller portion of the sky with more overlap between the fields of view in successive observations, and then there would be no problem finding habitable zone systems around K stars, as well as M stars, which we would continue to see.
So as anything involving orbits and transit methods with exoplanets, the longer you can observe the sky, the better, just to get more light curves. So that's really good. Let's see. Matthew Long is asking, would scientists using TESS be able to differentiate an object impacting a star from other sources, stellar vibrations? This goes back to your talk about astroseismology. Can you tell the difference between something hitting the sun, like maybe a comet, or?
Well, I think what you can say, what you would be able to see would be if it were just a single collision and then it only lasted a relatively short time, a few hours, it would be unlikely that you would see that. However, if it were something like a series of comets or asteroids striking the star over a period of several months' time, which there have been instances of systems like that Kepler has actually seen indications for. TESS would also be able to find those as well.
Okay. And they have a different structure in their light curve than something like the astroseismology would have. So that would go into light curve modeling to determine what was the source of what we were seeing.
I see. Okay, and sorry, fun dingles. I had to ask this question from Fun Dingles. Statistically, around red dwarfs, is it more likely to find rocky planets or gas giants? TRAPPIST-1 having 7 Earth-sized planets without any gas giants in the system seems odd.
My understanding is that actually Earth-sized planets are both more common and around M dwarfs. In fact, gas giants are rarely found around M dwarfs. Now that may be partly a selection effect if they're out as far as the giant planets are in our solar system. But in any case, there seems to be no underabundance at all of rocky planets around M dwarfs. In fact, on average, there are many more planets that they have, period. That's something like almost twice as many on average per M star.
I think it's one of the most exciting things about exoplanets right now is that we're actually able to talk about something like that, and we have real data to support it.
Right.
And you're saying that is starting to inform planet formation models. You know, is planet formation fundamentally different around a very low mass star like an M star versus a star like the sun?
There you go.
It's just a great
golden age, baby, golden age. That's right.
Golden age.
All right. Well, hi Galaxy. I'm glad you could make it back. We're having a lot of technical difficulties, but I'm glad you could make it. And then one last, I guess okay, Hans, I'll go ahead and make this comment for you. What about the people with tinfoil hats? Won't they say you removed all evidence of aliens if you edit the images before releasing it to the public? Now, this is actually something that has to be done for people to do science on the images at all. You've got to remove the instrument artifacts. You've got to calibrate them, right? I mean, you can't just put out raw data. Or are you going to put out raw data?
Well, the raw data will ultimately be delivered to the massed archive, but for most astronomers, that's not where the interesting thing is. They're not so interested in looking at the effect of little dust flecks that happen to be on the CCD or things like that we know aren't astronomical in character.
Well, I can't imagine why not.
But you know, Tony,
the data is going to be out there, right? Publicly available to anybody can get it. Yeah.
You know, Kepler, the K2 mission, just downloaded the TRAPPIST-1 data, and they made the raw data public as soon as they could. And teams are, they're chomping at the bit, getting their papers out, and calibrating the data at this point for K2 is well enough understood that you can trust those teams to do a pretty good job with the raw data.
So what are we looking at? We're looking at almost 10 years for Kepler and K2, aren't we? 2009 was when it launched, I think. So yeah, I think I've got that down a little bit now.
It launched in 2009, and they're planning out through like a campaign 17.
Wow, that's just amazing. That's an impressive thing. Okay, guys, thank you. I want to thank you for staying a little bit later. Before I go, one last question for you. Will you come back and give us another hangout just a little bit before launch to tell us how things are going, and let's talk a little bit more about TESS? Maybe?
That sounds delightful.
Sure.
Oh, great. Thank you,
All
guys.
right, we got them, Tony.
Yes, we do. Thank you guys very much. If you guys want to just leave the Hangout, just hit the red phone button up there. I'm going to stay live for just a couple of minutes to talk about what happened. And then, but you guys can certainly leave. Thank you both for your time. Alberto, you're
Thank
welcome
you,
to
Tony.
stay or go.
Yeah, I'll say.
Take it easy. Best of luck on the launch.
Thank you.
I will be there.
Thank you, guys. Thanks a lot.
Yes,
Bye-bye.
thanks. All
Bye,
right,
George.
thank you.
Bye-bye. Bye.
Okay, guys. So I'm sorry about that. But here's what happened. I went to go. Everything was set up. This is done on a Google Hangout on air, and Alberto can tell you we were sitting there ready. 3 o'clock rolls around, and I go to hit the start broadcast button, which is this big green thing at the bottom, and it wasn't there. I could not find it, and every time it just disappeared. There was no way for me to start the Hangout, and there was nothing to do. And this has happened to me with various difficulties on Hangouts on air so much that I'm working on ways of getting around it. There have been times when the Hangout quality has been poor, even though all of us have had good throughput in our internet connections. So I apologize for what happened. And I had to start a Hangout completely from scratch to get that button back.
All right.
And so that's what happened. I had to switch. But you know what, Alberto? We ended up with quite a bit of viewers anyway. I know we could have probably gotten more if we had stuck with our original thing. Hans is asking you, by the way, and we talked about it. We always ask this. So where did you get that clock, Alberto?
Maybe we should post the link to IKEA. It's a Lego. They're Legos. They are very different colors. Like we can post the link. Maybe I can send it to Tony or something. I just sent it to someone on Twitter, but and on IKEA, and then I just painted it gold. Obviously, it's actually a clock. It was kind of nice, and I wanted to buy more, but they don't make them anymore, guys.
Yeah, that was from IKEA. But so we might come up. Well, I should come up with something and maybe sell it. That'd be a big deal.
There are the mirrors, you can say. So I just sent you the link there. You can be on Amazon. It still says unavailable right now from IKEA. And I bought the last two in LA when I was there a while back. And one is now sitting at in Scott Willoughby's office at Northrop Grumman Aerospace System, who is the program manager for James Webb. I thought he should have one. And the other one is sitting behind me.
It lets me post links in the chat, guys, which I just did. You can't post links, but I can. So that link is what Alberto just gave me.
I mean, if you can find it somewhere else, please let us know.
Yeah, if you do find it at IKEA, or maybe, wait a minute, somebody is like, Buddy Lauder goes, we can all go to Denmark and buy one in Legoland.
Okay, yeah, there you go. Or we can do that, yes. We can actually buy a Lego model jet of his thing in Legoland, probably. I don't know.
Bike Jake goes, it's my first hangout. I appreciate it. Well worth any troubles. I'm so sorry about that. Usually they go better than this. Mavisimoy is going to be available on YouTube. I missed most of it. I thought it was supposed to start at 8 GMT. Yes, it's going to be archived at the link that you're watching now. You'll be able to watch it all. And again, so what I'm going to do to solve this problem, I've got Wirecast. I'm going to stream a different way to YouTube and simultaneously to Facebook and to Twitch. So we're going to be going to 3 different platforms. Maybe as early as next week, but probably starting with the Footsteps to Mars Hangout next month at the latest. So I'm getting away from Hangouts on air, just so you know. I just wanted to explain that to everybody and let people know. So thank you all for watching. Alberto, thank you for hanging in there and helping me out. You were a rock star as always, so I appreciate it. Thank you. All right, guys, I'm going to go ahead and cut the Hangout here. You should sell a clock for the ceiling so you have to keep looking up. I like that. All right, guys. Okay.
Until next time, man.
Alexia, you can watch it. It'll be archived here in about 10 or 15 minutes, so you can watch it on the same thing. I have a Twitch account. It's called DeepAstronomy. And is Tony in the Bay Area? No, I am in Florida.
Tony wishes he was in the Bay Area, but that's a different story.
Yeah, that's true. No, I'm in Central Florida near Kennedy Space Center. So anyway, thank you guys. Thanks for your patience on this, and thanks for hanging in there and trying to find us. Alberto, you going to come back at Footsteps from Mars? Yeah, we'll do. We'll try to make every chance I can. Yes, absolutely. Good to see you again, my friend. Thank you for joining. Take it easy, Tony. Take care. Bye. Bye. Oh wait. And thank you all for watching. And as always, keep looking up. Oh my God, this Hangout. Sometimes you look forward to these Hangouts and everything goes wrong. I was so psyched about this Hangout. And then, of course, that's the one I have technical problems. So anyway, see you guys next week. Oh, next week is also cool. We're going to be Carol Christian, Astro Coffee, 3 o'clock Eastern Time, Thursday. We're going to be talking about water on Pegasi 51, is it 51B paper on that. And so I'm excited about that one as well. Really good. I mean, these guys are up in their game, both Alberto, Carol, Harley, Alberto, all of them are really getting some great topics for us. So thank you all for watching, and we'll be doing that 51 Pegasus IB water possibilities next week. So thank you all for watching. Okay. Talk to you later.